We're going to define the derivative of a function in this section, and which will serve as the focus for a good chunk of our work going forward. And as it turns out, to define the derivative of a function, f of x, we're just going to revisit what we've already been working on when we were finding the slope of a tangent line. So the derivative of a function, one way to denote it is this way, right? So we read f prime of x when we see that, but it's this little tick mark here, right, that indicates that we're taking a derivative. And it is defined by this limit that we learned last time when we were finding the slope of a tangent line. It's important to note that f prime of x is also a function of x. So f of x and f prime of x, they're not the same function. They're related to each other, but they are not the same function. It is important to note that f prime of x is a function of x. There are other ways to denote the derivative. So let's say we have this function y equals f of x. Its derivative we can denote with just f prime of x, like we already talked about, or dy dx, which we haven't talked about yet, but this is probably the notation you'll see me use the most. But these two, and in fact maybe, and also the y prime, are used the most. So the f prime and the y prime, they're just like the same type of notation, right? So we could see why we might, if y is equal to f of x, we could see why y prime means the same as f prime of x. Now this notation here, this comes from how we encountered the derivative the very first time we looked at it. The motivating question for finding the derivative was finding a slope of a tangent line. And the slope of a line is a change in y over change in x. So it comes from sort of this notation, delta y over delta x. If you've taken, depending on how much science courses you've taken, you'll be aware that delta stands for a change. So change in y over change in x, delta y over delta x. And the idea is that as the delta x gets really, really small, which also causes the delta y to be very, very small, the smaller that gets, we just change it from delta x to dx. So dy dx denotes the derivative. This notation here really is where we see this d dx used kind of like as an operator on a function. So that just says take the derivative with respect to x of whatever's inside the brackets of that function f of x. And then this notation is not very common. You may not see that unless you kind of maybe look at some particularly older books. But I wanted to just make you aware of its existence. So we're going to do an example. Let's find f prime of x for this function. F of x is 2x squared plus 3x. We're going to do, what we did last time. If we're finding the derivative, then we're going to set up this limit. So we need an expression for f of x plus h. So we're going to replace x with x plus h. I'm going to do some algebra to expand this. Distribute that too. Oops. Distribute the 2, so that'll be a 4xh. So there's our f of x plus h. And in the limit that we need to set up in the numerator is f of x plus h minus f of x. So let's subtract f of x from both sides. And if we're subtracting f of x, then we are subtracting 2x squared and subtracting 3x. So minus 2x squared minus 3x. And I just like to kind of line it up so that the like terms are aligned. Now we have f of x plus h minus f of x is equal to, so let's see what doesn't cancel, right? So those are gone and those are gone. What's left is 4xh plus 2h squared plus 3h. So I've got this expression, and now I can set up the limit. When we find the derivative this way, we say that we are using the limit definition. And I'm bringing this up right now because in subsequent sections, we're going to learn some shortcut techniques. But whenever a problem asks you to find the derivative by using the limit definition, you have to set up the limit. Sometimes people will do a lot of the algebra and then they'll write the answer, but they don't actually write out what the limit is. So I'm going to start saying, okay, f prime of x, this is the limit as h approaches 0 of f of x plus h minus f of x all over h, and this is the limit as h approaches 0 of, well, the stuff on top is 4xh plus 2h squared plus 3h all over h. I have to carry the lim all the way through. I have to do that right up until I let h be 0. Now I can't let h equal 0 at this point because I have a factor of h in the bottom. So I'm gonna, let's see, observing at the top here, every term has a factor of h. So I'm gonna factor out an h. Now we can cancel those h's. And now, look, it's no longer a problem to let h approach 0. In this expression, if h approaches 0, then this term in the middle, the 2h, will approach 0. And then we're left with 4x plus 3. And this function is the derivative of f of x. So this is f prime of x. It is, if we wanted to, we could use this function, f prime of x, to help us find the slope of a line tangent to the curve for f of x at some given point. So the last one was a polynomial, and all of the ones we did in the last section when we were working with slope of a tangent line were polynomials. So, and those pretty much all go the same way, right? I mean, we know we're going to have to expand. We know that when we're done expanding, the f of x plus h, and then when we subtract f of x, we know that this expression, if f of x is a polynomial, by the time we're done that process, everything, right, should have a factor of h in it. And then we're going to factor it out, and it'll cancel, and then we can let h go to 0. So if our function is a polynomial, it isn't, we know what to expect, I guess. The algebra is pretty straightforward. So what we're going to do now is look at some functions that are a little bit different. And in this first one, we're going to see what do we do when we have x's appearing in the denominator. So here's an algebraic fraction. Y is equal to 3 over x plus 2. We're going to find the derivative. We're going to find the derivative f prime of x, or dy dx. That's a function of x. And then once we're done that, we'll evaluate it when x is 1. So f of x plus h. Well, I'm going to replace x with x plus h in the original function. So let's see. This is our f of x function. And if I replace x with x plus h, it looks like this. Right, instead of x plus 2 in the bottom, it's x plus h plus 2. Now, let's find f of x plus h minus f of x. So this will be 3 over x plus h plus 2 minus 3 over x plus 2. All right, now maybe take a second if you want, pause the video and think about, how would I approach this algebraically, knowing that our goal is to be able to set up that limit and let h approach 0. All right. So what we need to do is some algebra, and we want to write this as a single fraction. We have to be careful with our algebra, and we need to understand that x plus h plus 2 and x plus 2 have no common factors. No common factors at all. So if I want to get a common denominator, I got to multiply the first fraction on the top and the bottom by x plus 2. And the second fraction, I have to multiply the top and the bottom by x plus h plus 2. All right. Sometimes people want to say that, oh, it looks like the second fraction is just missing an h, so why don't we throw that in? But it's not missing a factor of h. This first denominator does not have a factor of h. H is just a term that appears in there, right? And we need a common, the greatest common, or the least common denominator has all the same factors, not all the same terms. We can't add terms in, right? We can only add factors. So, doing the algebra here, our common denominator is x plus 2 times x plus h plus 2. And up top, I'm going to have this product minus that product. I'm going to expand the numerator, and I'm going to keep the denominator factored. This is a general advice when we're doing limits in this way. Just keep the denominator factored. In fact, when you're working with algebraic fractions, there's usually not much of a reason why we would multiply out the denominator anyway. So we're going to keep denominator factored. But we're going to expand the products in the top. And that's because the top we don't have written as a single product like we do with the bottom, right? Because, of course, we've got this subtraction. So in order to simplify the top, we actually need to expand those products and combine like terms. Alright, so up here we've got 3x plus 6, and then I'm going to distribute the 3, and in fact really it's the negative 3 because we're subtracting that whole thing. So minus 3x minus 3h minus 6. Now examining the top, we can combine some like terms. 3x minus 3x, those cancel, plus 6 minus 6, those cancel, and the only thing we're left with is that minus 3h. Okay, now we've done a bunch of the algebra and we're ready to set up that limit because, of course, when we're finding the derivative of a function using this limit definition that we know, we have to set up the limit. So dy dx, the derivative, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is the limit as h approaches 0 of, now it looks like, right, we're going to have a fraction as the numerator of our fraction. So that's what we have right now to start with, but we're going to clean this up. Now dividing by h in the bottom here is the same as multiplying by 1 over h. So that's how I'm going to write it. And once I do that, I see, of course, I can now cancel this factor of h with that factor of h on top. And we want to evaluate the limit as h approaches 0 of the fraction -3 over x plus 2 times x plus h plus 2. Now, if you're looking at this fraction, at this limit, and you're saying, well, we still have an h in the denominator. That's true. We have an h in the denominator, but it is not a factor of h. If h is 0, it does not make the whole denominator 0. So we're actually in really good shape. In fact, if we look at that factor, we can observe that as h approaches 0, x plus h plus 2 approaches x plus 2. Right? We're just letting that h term go to 0. So now let's let h go to 0. Now is when we don't have to write lim. We got -3 over x plus 2 times x plus 2. And of course, we probably simplify that and just call it -3 over x plus 2 squared. There's our derivative. That's the first thing they asked us to do, and it's the thing that takes the most work. Now, as a follow-up, we're just going to kind of reap the fruits of our labor here and evaluate this derivative when x is equal to 1. Now, just a little bit of notation. When we evaluate when x is equal to 1, using the Dydx notation, the way we indicate that we're going to evaluate this at a particular value is we draw this little vertical line, and then down here as like a subscript, you write x equals, and then in this case it's x equals 1. So I'm replacing x with 1. This is -3 over, let's see, 3 squared is 9. So this is -1/3. So with the Dydx notation, this is how we indicate we're evaluating it at x equals 1. Or if you're using the prime notation, you could say f prime of 1 equals -1/3. Right? They mean the same thing. And of course, you know, we've been defining this for the function f, but the prime notation works regardless of what you're calling your function. So if your function is g, then it's g prime. If your function is h, then it's h prime, right? So whatever letter you use to define your function, that's what you put the prime on, or, you know, same with the Dydx. All right. We know what to do with polynomials. We've seen an example of how to work through a function where x's are in the denominator. Now we're going to see how do we take the derivative of a radical. And we're going to illustrate our approach to these types of functions, and that should work for, you know, it should be effective for any function that's a radical. So this is, we're looking at the square root of x, but if you had y equals the square root of 2x minus 3, then it should also work in that case as well. So, let's set this up. So here's our, you know, this is our f of x function. Our y is our f of x. So f of x plus h means replace x with x plus h. This is the square root of x plus h. And that means that f of x plus h minus f of x is equal to the square root of x plus h minus the square root of x. Now last time, you know, when we were working with the function that was a fraction, right, where we had x's in the denominator, once we just set up the difference, right, once we saw the subtraction, we said, oh, you know, we can do some algebra, let's get a common denominator. And we had a pretty clear algebraic path forward. And that's not where we're at here, right? We can't combine radicals under subtraction. There's no obvious algebra to do right here. So we're going to just continue by setting up our limit. So dy dx, this is the limit as h approaches 0 of f of x plus h minus f of x all over h. So we have on top the square root of x plus h minus the square root of x all over h. Now we're in a bit of a bind here, right? We can't let h go to 0 or we'll be dividing by 0. There's no obvious algebraic path forward to simplify the expression up top like we have with the fractions. So right now what we're going to do is use a technique we used to use to help us work with radicals, radical expressions. And I'm going to just up in the margins here remind us. Let's sort of have a little flashback here. When we were working with radical expressions in pre-calculus, one of the things we do is, rationalize the denominator. And if I had an expression like, I don't know, 1 over root 7 minus root 5. And if we wanted to avoid having radicals in the denominator, we could rationalize the denominator here by multiplying the top and the bottom by the same thing. And that same thing was the conjugate of the denominator. So that just means whatever that operation is in between, flip that operation and multiply on the top and the bottom. So we'll multiply by root 7 plus root 5 on the top and bottom. So up top, it's pretty clear we have root 7 plus root 5. And on the bottom, we just have to FOIL this out or expand that product. So that would look like root 7 minus root 5. I'm just going to set up the little grid here. Root 7 plus root 5. So across the top row here, we've got 7, and then minus root 35, because we can combine radicals over multiplication. And then on the bottom row, we have a positive root 35, and then, let's see, the last entry, a negative 5. So these terms here, those cancel, right? A positive root 35 and a minus root 35. And then these are like terms. 7 minus 5 is equal to 2. And look, that process allowed us to rationalize the denominator, so we don't have any radicals there. Where that, what does that have to do with this example? When we're setting up this limit to find the derivative of this function, what we're going to do is rationalize the numerator. So we're going to multiply the top and the bottom by the square root of x plus h plus the square root of h. The square root of x. Now on the bottom, we just have this product. I'm going to leave it factored. There's not usually any advantage to multiplying out the product you end up with in the bottom. Up top, we're going to expand that product just like we did in the example above in the top margin. So I'm going to do, I guess, some of this work over here. Let me sort of block out some space here. So I want to find that product. I've got root x plus h minus root x, and I'm going to multiply that by root x plus h plus root x. Now across the top row here, a radical by itself, that'll just be x plus h. Then we have minus root x times x plus h. And then on the bottom row, we got a positive root x times x plus h. And then at the end, at the last one, we've got a negative root x times root x is x, so minus x. These terms cancel, right? Because they're the same, or they're just the opposite signs. And when we combine those like terms, we have x plus h minus x. And that is just h. So that's what goes in the numerator here. And now, I think we can see our path forward here. I mean, we can cancel that factor of h. Now, when we cancel the factor of h up here and there's nothing left, there's actually a factor of 1, right? That's what we'll replace it with. So this is the limit as h approaches 0 of 1 over the square root of x plus h minus the square root of x. Now, we're in a good spot to let h be 0. Again, we see that we still have an h in the bottom, but it's not a factor of h. If h becomes 0, the denominator does not become 0. In fact, we could see that as h approaches 0, the square root of x plus h approaches the square root of x. So let's let h go to 0. We no longer need to write lim. We have 1 over, oh, and for some reason I wrote a minus here when it should be a plus. Let me fix that. So we have root x plus root x. And of course, we should simplify that. That's just 2 root x in the bottom. 1 over 2 times the square root of x. That is dy dx. Or y prime, if you like the prime notation. All right, one more here. We've got a function with a couple of terms. One term is like a polynomial term, 4x cubed, right? If it were just y equals 4x cubed, this would be just like the simpler ones in the beginning. Expand, cancel, and, you know, then you can let h go to 0. The second term is a fraction where we have x appearing in the denominator, and we learned how to deal with that earlier in this section. So let's set up let's do some algebra here. F of x plus h is 4 times x plus h cubed plus 5 over x plus h. I'm going to expand that x plus h cubed. You might remember from the last section, we spent a little bit of time talking about Pascal's triangle and how we can use it to help us expand this. So when you expand x plus h cubed, you're going to get x cubed plus 3x squared h plus 3xh squared plus h cubed and then we can distribute that factor of 4. Alright, so here's f of x plus h. Now let's subtract f of x. So let's subtract that original function. And if we subtract f of x, we're going to subtract 4x cubed, and we're going to subtract 5 over x. So over here on the right side, right, we're going to do some combining of like terms. There's very little combining of like terms, but we can cancel the 4x cubed with a negative 4x cubed. So we end up with these terms. Now 12x squared h plus 12x h squared plus 4h cubed. And now we have the two fractions, plus 5 over x plus h minus 5 over x. Now there's more than one way. I guess we have a couple of options here for how you want to proceed. Some people like to get the whole function, right? The whole, like, f of x plus h minus f of x, this whole expression written as a single fraction with a common denominator. And you can do that. I think it's simpler to just get a common denominator for the two terms that are fractions. You know, the three terms in the beginning, those all have a factor of h. I like the way that looks. I'm just going to leave that as it is. I'm going to get a common denominator around between these two fractions at the end. So the first fraction has to pick up a factor of x. The second fraction has to pick up a factor of x plus h. So we got 12x squared h plus 12xh squared plus 4h cubed plus, now I've got a single fraction. The denominator is the product x times x plus h, which I'm going to leave that as it is. And then I have 5x minus 5 times x plus h. We're going to expand the numerator and combine like terms. So distributing that minus 5, we got minus 5x minus 5h. The 5x and the minus 5x cancel, and we have just minus 5h. Now, we're ready to set up this limit. I just want to point out, though, first, and it might be helpful to actually write it out, take one more step before we set up the limit. I just want to point out that every single term now has a factor of h. So I think it'll actually help if we factor that out now before we set up that limit. At least for me, it kind of will help organize and streamline the rest of this problem. So I'm going to take out the h. So now what we have is 12x squared plus 12xh plus 4h squared. I guess instead of doing plus and minus, I'll just call that minus 5 over x times x plus h. All right, now let's set up this limit. So dy dx is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Up top, I've got this product of h times 12x squared plus 12xh plus 4h squared minus 5 over x times x plus h. So those h's cancel, right? We saw that coming. And now that we don't have a factor of h on the bottom, we should be all set to let h approach 0. Let's see how this looks. Okay, so as h approaches 0, any term with a factor of h will approach 0, right? The 12xh, that goes to 0. The 4h squared, that goes to 0. And this h by itself goes to 0. So as h approaches 0, x plus h approaches x. So let's let h approach 0 now. And we no longer need to write the lim. So we have our first term, 12x squared. The next two terms 0 out. And then minus 5 over, the bottom is x times x, or x squared. There's our derivative.